All right, can you see the slides? Alrighty. So we stopped here yesterday. We discussed about a thick diode current and thick diode versus thin diode. Yeah. So the journey starts yet today kah? Apa Cornelia? Mulai hari ni pergerakan student. Oh, yesterday. Okay. So it's today sampai yesterday sampai sometime next week is it? Or all this week? Till Thursday, so all this week lah. Okay then. So apalah, what to do? Hope they can watch the recorded version later on. So let's continue anyway. We stop here after discussing about the current density due to diffusion, right, which is dominant in the quasi-neutral region. And we have been discussing about the minority carrier density, so diffusion current density associated with the minority carriers in both sides of the QNR. Okay, so that's why we need to use JHX on the right hand side in the n-type, so for the holes, and on the left hand side in the p-type we need to use JEX, right, because holes in the right hand side is the minority carrier in n-type, and electrons are the minority carriers in p-type on the left hand side. And yesterday we've also discussed about the magnitude of the current density in the quasi-neutral region. If you look at this profile, the JHX profile and JEX profile, if you look at those two profiles, the change of current density, the change of current in the depletion region will become negligible, right? The change of the current in the depletion region will become negligible because they are very, very small in this small region. Okay. And we assume that the depletion region is small by its nature. So typically it's about 1 micron or so, or even narrower than 1 micron. So out of the whole thickness of the wafer that we normally use. Okay, so we discussed this one yesterday as well. So say your device thickness or the wafer thickness is about 200 micron. So we normally form the junction on the front side normally, but not necessarily. It can also be at the back, can also be both. But for simplicity, let's assume that we form the junction on the front side. We form the junction on the front side, typically with thickness of about 200 nanometer or so, right? The thickness is only about 200 nanometer. Also, right? This is very, very thin in comparison to the whole wafer thickness, which is about 200 microns. So that's about 1,000 times smaller, right? Nanometer to micrometer for the same magnitude, 200. So 10 minus 9 to 10 minus 6. So that's about 1,000 times smaller, more or less. So if you talk about this p-n junction, say the front side is n-type, n-type, the wafer is p-type, so the depletion region will be somewhere there. Very, very small region in between this junction. Okay, so normally that's about, this is the W that we're talking about, here, right? So that's about 1 micron or so, or perhaps thinner than that. So it depends on the depletion region width that we have learned to calculate last time, which depends on many other parameters. So because W is small, the change in current across the depletion region is also small. That is delta JE and delta JH, and both are assumed to be close to 0, right? In comparison to the current profile in the quasi-neutral of N and quasi-neutral of P, right? So we assume no recombination in the depletion region as well for simplicity. But in the actual PN junction devices, there will be recombination in the depletion region, okay? And that will change the equation that we're going to work on. So since this is the case, since we assume that these two are close to 0, then we only need to solve for a minority carrier current in each of the N-type and P-type. So both in P-type and N-type regions only. We don't have to worry about the depletion region current because we assume them to be 0 to begin with. Because the recombination of minority carriers determines the current flow. Okay, it's recombination of the minority carriers, which is this, and this determines the current flow. Right, so J total, we discussed before about this. J total current. Total current is given by JEX times JHX, right? It's a constant there. You can see on this page, JEX and JHX. And that is given by this Q and P naught times D over L for electron plus Q P and naught plus D over L for holes times exponential component of this, exponential of QV over KT minus 1, right? So these can be then simplified to be the below equation. J equals to J naught exponential of QV over KT minus 1, right? And this is called diode equation. It's called diode equation. So we mentioned briefly about diode equation yesterday, where you've learned a little bit in electronics, and this is about the inside of that, right? So if you talk about holes in N-type region that we mentioned before, so the JHX here is given by this, right? By this equation. So if you talk about electrons in p-type, so you're going to use this very same equation, but you're going to flip the parameters, say from DH to DE, right, for electron. And then this one, the minority carrier, is also the inverse one. LH becomes LE, and then this one becomes LE as well, right? So this is the ideal diode law, where if you extract this J naught is the saturation current density, diode saturation current density in ampere per cm squared, and that is given by this equation, right? Q times D over L NS squared over NA plus Q times D over L for holes times NS squared over ND. So this is saturation current density. So note that the J naught is small for large diffusion length. So if you look at this equation, J naught is small if you have a large diffusion length and large doping levels, right? Large diffusion length and large doping levels on both sides, and for large band gap material as well. So J naught is the most important diode parameter. So J naught here, from this equation, we can see that J naught is small for large diffusion length. So J naught is proportional to 1 over L, or inversely proportional to L, if you like. And J naught is also proportional to 1 over N, right? NA or ND, yeah? Either one is fine. As long as you have the doping level to be high, then J naught will be small. So this is called diode saturation current density, or also called leakage current, right? J naught is also called leakage current. So based on your understanding in electronics last time, do you want J naught to be high or to be low? Do you want J naught to be high or to be low? Saturation current density or leakage current? If you talk about leakage, do you want your leakage to be high or to be low? Anyone? Ini apa ni? Saya lukis ni. You see air dalam baldi, water bucket, right? Water bucket. So you have water there. So the analogy is the same. So water bucket. Then kat belakang ni you ada leakage. Air menitik. Baldi pecah lah. Simple analogy is the bucket is leaking. So do you want the leaking to be a lot or little? Or no leaking at all? Low, right? So the principle is the same. I've read, I think one online reference somewhere, I couldn't remember. I'll try to find for you later on. That shows exactly this example, the water bucket analogy, right? So the current that you have is like the water in the bucket, and then at the same time, if your device has some leakage, you're gonna have the water leakage leaking from the bucket. Dekat belakang, at the back or at the side or whatever. That there are holes somewhere in the bucket that causes the water to leak, and the leaking water is like the J naught. Leaking water is like the J naught, right? If I could find the reference again, I'll show you. I'll put on e-learn later on, right? So the leakage current is like the J naught, and what you have in the bucket is like the J, right? The J from the diode equation there. So if you look at the diode equation, J equals to J naught exponential of Q EQV over KT minus 1. And you want to keep the J naught to be as low as possible, right? So how to keep it low? You can come to this J naught equation, right? So we know that J naught is inversely proportional to L, diffusion length, and J naught is also inversely proportional to NA or ND. Okay, sama juga the same goes to the LE or LH, right? If you like, because there are two components for electrons and for holes together as a total. So as long as you can ensure that your diffusion length of the carriers are high, are long, then your J naught will be low. Or if you dope your device to be high, say 1018, 1019, rather than 1016, 1015, for example, in this case, then you can keep your J naught to be low as well. But when it comes to the actual semiconductor devices, it's not only one-dimensional kind of thing. So it's not like you do one and you solve everything. So you do one, you solve something, but you're gonna end up with some other different problems, right? We're gonna see later on. And in fact, we've seen already last time when you dope your semiconductor to a very high level, what do you have? What problem arises? Right? Remember last time we discussed you want to dope your semiconductor high so that it's very conductive, but what's the but? Let's recall what we learned before. Degenerate, okay. What else? Say you can dope 1016, and then to improve conductivity, you want to dope like 1019. So that the electrical conductivity of your material or of your device improve. But then the problem is, what is the problem? Say 1016 over versus 1019. 1019 improves conductivity, but it comes with what? Anyone? Anyone? Faris? Any idea, Faris? Any idea? What happens at a high doping level? Yeah, lattice scattering, good. Yes, lattice scattering because of the impurity, right? Impurity, right, Joanna? So you have more and more impurities, and then there's going to be a lot of impurities in the lattice, and the carriers are going to be scattered by the by the impurities, right? So impurity scattering, Joanna, instead of the lattice scattering. Lattice scattering is more of the temperature, more related to temperature. If you supply the heat to the lattice and then to the material, and then the lattice vibrates, and then the kind of the lattice scattering, more enhanced lattice scattering. But if you put more dopants in the lattice, it's going to be more impurity scattering, assuming no change in temperature. Okay, apa lagi? What is the other but? You improve conductivity at higher doping, but remember, what's the word? Starts with R. But the problem is we have enhanced R. Apa R? Mula huruf R. Baru je belajar, few weeks back. Anyone? No, resistivity tak. Resistivity akan reduce kan. You increase the doping, resistivity will reduce because the conductivity improve. Yes, recombination, right? So you increase your doping level, recombination increases. So to be more specific, which recombination increases? So we learned about the 3 recombinations, right? So to be more specific, which one increases? As you increase your doping level from 1016 to 1019. Traps, yes, traps. You increase defects if they are defects. What's the prominent one out of 3? What's the most prominent one out of the 3 recombination mechanisms at high doping level? What? Lupa lah. OJ, right? OJ recombination, which dominates beyond 1017. Okay, so if you go to 1019, in order to improve conductivity, it comes with increased recombination as well. So increased recombination will somehow lead to increased J naught as well. So kalau you tengok equation ya, if you look at this J naught, okay, tengok yang ni ya. J naught is inversely proportional to L. J naught is proportional to 1 over L. Either way is fine. Sama aja. So L is what? Diffusion length, right? So if you have more recombination, do you have high diffusion length or low diffusion length? So if you have more recombination, do you have high diffusion length or low diffusion length? Are you sure, Amirul? You have more recombination. Do you have high diffusion length or low diffusion length? What is recombination? Carrier recombine, right? So carrier recombine, does it survive long or does it survive short? Terbalik kan? You have more recombination. You are being attacked everywhere from every angle. So your lifetime shortens, right? Lifetime shortens, then the diffusion length reduces as well. So when the diffusion length reduces, what happens to the J naught? When the L reduces, what happens to the J naught? By this relationship, increase, right? J naught increases. J naught increases. So when you have more recombination, your diffusion length increases. Diffusion length of the carriers, it reduces because of more and more recombination. Lifetime there is very short. Then when lifetime is very short, L is equal to square root d tau, right? Tau is short, L is short, therefore J naught increases. Okay, so when you have more recombination, you're gonna have shorter diffusion length, hence higher J naught, right? Higher J naught is undesirable. You want to minimize the J naught. You don't want to have high J naught, right? Just like the leaky water. You don't want to keep pouring water into the bucket at the same time it goes out the back, right? Buang masa. So it's not productive, it's counterproductive. So the same thing happens with J0 as well. So it's like counterproductivity happening there. All right, so consider the path of electrons and holes through the circuit. So this is the illustration of what's actually happening in the quasi-neutral region and also diffusion region. So in the bulk, most of the current is drift as there's no gradient in the concentration, right? There's no concentration gradient. Well, you can also argue this because we learned last time that electric field is the strongest in the diffusion region, but it's very, very weak in the quasi-neutral region, but it's not zero, right? So the moment it's not zero, you're going to have the drift component as well. So because drift presence due to electric field. As long as you have electric field, you're going to have drift. It doesn't matter what's the amount like, right? The higher the electric field, the higher the drift. So as we approach the junction, carrier concentration change, and we get a combination of drift and diffusion. So the moment we are close to the junction, we're going to have higher electric field, therefore higher drift, and the carriers are going to start seeing concentration gradient near the depletion region, near the border of the junction, and therefore we're going to have diffusion as well. Drift will dominate for majority carriers. Note that the electric field in the neutral region cannot be zero as we assumed last time, like we assume it's zero, but it's not zero in real life. But since we have a large majority carrier concentration, the field is not large, right? The field is not large, but it's not zero. So but the minority carrier parameter D over L is equal to S. Right, this S is actually surface recombination velocity. Okay, surface recombination velocity, or we normally call it as SRV, surface recombination velocity, right? Has the dimension of a velocity and can be considered as the bulk recombination velocity. So we can call it as bulk recombination velocity or surface recombination velocity depending on what we are looking at, right? So if you talk about the bulk, then it's bulk recombination velocity. If you talk about surface, then surface recombination velocity, right? You can call it BRV or SRV if you like. Okay. So the unit is centimeter per second. Right. So for good quality silicon, so if you talk about good quality semiconductor material, your D over L or S is typically in the range of 300 to 600 centimeter per second, regardless of doping level and type. So you want to, if you talk about the recombination velocity, you want to keep the recombination velocity to be low. Okay. So we want it low. We want low, right? So if you can imagine like this, if you have your recombination velocity to be high, and then you're going to end up with more recombination. If, on the other hand, if you have a low recombination velocity, either bulk or surface, you're going to end up with less recombination. Okay, so in this case, we want the the bulk recombination or the surface recombination velocities to be low. So typically for a good material, it's in the range of 300 to 600 centimeter per second. So if you compare 300 to 600 centimeter per second with, for example, 10,000 centimeter per second, which one is better? Which one can be found in a better material? Which one is a better material? The one with 300 or the one with 10,000 centimeter per second? Which one indicates a better material quality for your device? Right, 300, okay? So if you have two different materials, one with a recombination velocity of 300 and another one with 10,000, so the one with 300 has a better material quality. right? The one with 10,000 has poorer material quality for a device, right? Okay, it can be shown that the resulting diode law is also correct in reverse bias. So let's see the diode law now. The equation, right? So you learned about this in electronics last time. So what you learn is just this equation, but what we learn in this course is beyond that, right? So you can even see this relationship from the diode equation, for example. So when we talk about a device later on, if we talk about a PN junction device, we're going to see the value of J and the value of J naught in the device. And then we'll see how much is good and how much is not good. What sort of level that we're talking about for a good PN junction devices. Okay. So this is a JV curve. Some people call it IV curve, right? JV curve, J because it's current density. Kalau I currentnya kan. So J is ampere per cm squared, if you like. Ampere per meter squared pun boleh juga, depending on what you want to see. So ampere per cm squared, so therefore we call it as current density and J. So we call this as a JV curve. So forward bias is when the voltage is in positive region. Reverse bias is when the voltage is in negative region. Okay, so this is increasing J, if you like, with increased voltage. So if you talk about silicon, then you're going to have, pernah belajar the knee voltage? Have you ever learned about knee voltage for silicon and others? No, have you learned about this, the knee voltage? No? For silicon, the turn-on voltage, right? The turn-on voltage. For the diode, because remember this is a diode law, so PN junction is a diode, right? Turn-on voltage. To be able to turn on the diode, so remember PN junction, PN is a diode. That's why we learn about diode equation, right? So PN junction is a diode. To turn on the diode, you want to turn on the diode needs at least 0.7 volt for silicon, right? If you supply voltage of less than 0.7, it will not be turned on, right? So it requires 0.7 volt in order for it to turn on. Kalau nak pakai diode dalam circuit, then it requires at least 0.7 volt for it to turn on. Okay, so that's called the knee voltage ataupun the turn on voltage, if you like. Okay, reverse bias is when it's negative, and J naught is here. J naught is this small region. If you zoom into this region, like the zoom into the JV, then if I exaggerate a little bit, let me just exaggerate a little bit. J naught is going to be here, right? This magnitude is J naught in negative region. So that vertical part in the negative x-axis, so that's the J naught, right? The very small amount of current there. So that's J naught, leakage current. So you want to keep that to be low, right? You want the J naught to be low. Kalau dia besar, so if you see it's very wide and big, then that means your device is not good. Your diode is not good. So diode IV characteristic or diode JV characteristic, if you like, boleh ya. In the dark, diode is as a rectifier. Apa maksud rectifier? What is a rectifier? You learn from electronics, right? Anyone? Diode as rectifier. Apa maksudnya rectifier tu? AC DC. Okay, elaborate a little bit. Haziq. Enhancer turns AC to DC. Okay. So, how does it turn into DC? How does it turn the AC to DC? Macam mana tu? Haziq? Serious? How does it get to be DC? Remember apa dia punya label diode? Allows current to flow one way only, right? So it only allows current to flow one way. Okay, diode flow, current flow ke mana? So if this is your diode, is the current flowing left to right or right to left? Is it flowing left to right or right to left? Okay, left to right current. Okay. So right to left, can it flow? Can it flow right to left? Cannot, right? So cannot. So that's why it's called a rectifier. Only one way. So it can flow from left to right, but cannot flow from right to left. So if you talk about this diode, for example, at circuit level, based on your electronics knowledge last time. So if you talk about this, so where do you supply the positive voltage? Which one has to have left side or right hand side yang perlu ada higher voltage for the current to flow? Anyone? So ni a left hand side. So I draw left hand side, just a box, for example, just to show. So which one do you supply higher voltage, left side or right side for the current to flow? Cameron say left. Betul Cameron, why left? So you need to supply higher voltage on the left and the right hand side is low voltage, right? Is it? Betul Cameron. Current flow from higher voltage ataupun from lower voltage? Okay, baru ada potential difference. Okay, how about you supply negative voltage on the left, positive voltage on the right? Will it flow? Cameron, why not? You said potential difference, yes. Potential difference, as long as you supply one side higher, one side lower, you're going to have potential difference, right? So if you said potential difference, then it could be either way, isn't it? But why does it have to be higher on the left hand side than the right hand side? Current flow from positive to negative. Yes, current flow from positive to negative, kan? Conventional current flows from higher voltage to lower voltage. Due to potential difference, it's going to push the current to flow. What else? If you look at the diode properties, the PN junction properties, if you put your positive voltage on the left and negative voltage on the right, are you forward biasing or reverse biasing? Positive on the left, negative on the right. Look at the box yang saya lukis tu. Positive on the left, voltage, I'm talking about the voltage, and negative on the right. So are we forward biasing or reverse biasing? The junction. Are you sure? Haziq? Forward ke reverse ni? Ramai forward, ada cakap reverse. Tak sure. Right. Ni you have to recall electronics. Diode punya simbol, yang mana positif? Kiri ke kanan? Based on the arrow you hentam je, right? So if you look at the arrow there, arrow of the diode, which one is the positive side? Which one is the P side? Kalau kita relate with PN junction, which one is where is the P and which one is the N? We try to relate with the real device. Sekarang kita belajar, we've been learning about the inside of the junction. Now we're gonna relate to the outside so that we understand. So P is left or right? Left. And right. Okay. So relate back to the above diagram. If you put the positive to the left, negative to the right, are we forward biasing or reverse biasing? Positive to the left, negative to the right, forward biasing. Forward, right? So if you forward bias, can the current flow in a diode? Can the current flow in a diode when you do forward bias? Yes. Yes, right? So if you look at, if you relate this connection stuff, blah, 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 with this JV curve, where is it on the curve? Where is it on the curve that we're talking about now? Forward biasing the diode, the junction, so that the current can flow. So where is it on the curve? Anyone can point to me on the curve? Where are we on the curve? Can someone say something? Which one? Where are we on the curve? I want to relate the, yeah, okay, right side, right? Forward bias region lah kan? We're talking about this region onwards. We are forward biasing the junction, forward biasing the diode, right? So therefore, we are on the right-hand side of the curve. So if the voltage supplied exceeds 0.7, which is the turn-on voltage for the diode, you're going to have a current flowing exponentially like that, okay, in the diode. Okay. So on the other hand, if you come back to this schematic kat bawah ni, ataupun kat atas ni, if you reverse the polarity, if you put negative on the left, positive on the right, where do we get? What do we get? Reverse biasing the junction, right? So where are we on the curve? Left-hand side, right? So we are now moving on the left-hand side. So we're reverse biasing the junction. So when you reverse bias the junction, is there any current flow? Do you have any current flow on the curve? Okay, no, go say no. Anyone else? Do you have any current flow at all? Just when you apply the reverse bias, kita dah belajar the junction, right? So what happens to the very high? So I want to relate the inside of the junction with the outside at circuit level so that you understand, so that you can relate what is going on at carrier level, junction level, and then when you measure the JV curve, what do you get? And why is it so? So do we get any current to flow on the reverse bias mode? Ada current tak? Tak tu? Tengok on the left side ada current tak? Can you see any current at all? Ada. You don't get conventional current flow, right? There's no current flow. So you're going to get something like this. However, so you're going to get a leakage there, right? So this determines the quality of the diode. You're going to get a very small leakage in the reverse bias mode, okay? So this will determine the quality of the diode. So if your diode is of high quality, then your reverse leakage current will be very, very small. If your diode quality is not so good, if your fabrication is not so good, handling and blah, 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 is not so good, the material is not so good, the J naught will be relatively higher in comparison to a good diode. Okay, so that's the whole point. So now do you see what happens when you apply forward bias? Last time we learned about when you apply forward bias after being at thermal equilibrium, we reduce the barrier height, carriers can now diffuse, and you can get current to flow, right? So as a result, you're gonna get this curve when the voltage is exceeding the turn-on voltage of the diode, say at 0.7. On the other hand, if you supply a reverse bias to the diode, we are actually increasing the barrier height further, and there's no current can flow, and there's no current actually. It's actually flowing through the diode. However, you're gonna have a recombination current, a leakage current through the diode yang akan cross juga. They will actually cross the junction as recombination current. If you come back to this, okay, you can see this recombination thing. Recombination. So these are the contributors to J naught, right? So these are the contributors to J naught that you see on the JV curve. See? So it's due to this, the recombination mechanism despite the reverse bias. So for a good silicon diode, J naught is theoretically in the range of 10 to the minus 10 to 10 to the minus 13, right? Very, very small. So that's about what? Nano pico m, nano pico m per cm squared. The typical range of J naught for a good silicon diode, right? So if you have a bad diode, for example, the J naught can be, say, up to micro m, 10 to the minus 6, right? Bad diode, it can be up to micro m, usually. Oh, okay. Sorry, can you still see the slides? Ah, okay, hold on. Discard block, is it like this? Okay, so as V approaches negative infinite, so negative, if you go to negative, a high negative, if you like, V approaches negative infinite, which means a very large reverse bias voltage. So the exponential term in the diode equation becomes zero. This exponential term becomes zero. So your J naught, your J will be equal to J naught, right? Negative J naught. If you go to high negative voltage. Oh, tak sempat nak buat calculation ni, 10:45 already. What time is it? 10:45. Tomorrow is Wednesday. I think we're just going to continue this tomorrow. So please try this question first, and then we're going to discuss tomorrow, tomorrow class, okay? Sekarang tak sempat nak continue. So tomorrow I'm going to move on to thin diode current to discuss about the effects of a thin diode in comparison to thick diode, and then we're going to move on to the calculation here. And then if the time permits, we're going to continue to PN junction under illumination. Okay? Is it okay for now? Okay, guys? Can you follow so far? Okay, good. All right, then. I'll see you tomorrow. Bye-bye. Take care. Assalamualaikum.